name is Jackie, and welcome to my Physics 2212 Lab 4 presentation. The purpose of this lab was to learn how resistors and capacitors affect parallel and series circuits, and to calculate potential difference and conventional current. The fundamental principles we used in this lab is Ohm's law, which is voltage equals current times resistance, capacitance, which is equal to charge over voltage, and the loop rule, which shows that the sum of potential difference within the circuit equals 0, and the node rule, which is current in equals current out. In the first part of the experiment, we created a series circuit with 2 volts, two 1.5 volt batteries, 2 ammeters, 1 resistor of 47 ohms, and 1 resistor of 100 ohms. As seen, the 47 is here and the 100 is here. And we were able to calculate that using the Ohm's law, we were able to calculate we were able to predict that the current would be equal to 0.02 amps, and as you can see from our diagram, the actual current is 0.02 amps, and if you were to reverse the ammeter, then the current would be equal to negative 0.02 amps, so the current would just be flipped. In the next part of this experiment, we created an open circuit, and we hooked up the battery to we hooked up the voltmeter to the current to see what the voltmeter would read, and you could see the current would be equals to 0 in this part of the ammeter reads that the current is equal to 0 in this part of the its circuit, because since the circuit is not connected or is not closed, current is not able to flow through here. And when we connected the voltmeter, we found that there were 3 volts in this left side, and 3 volts in this left side and 0 volts in this side, and the current is not able to flow through the voltmeter because the voltmeter's resistance is equal to infinity. And so in the next part of the lab, we had to calculate potential differences in different parts of the circuit, and as you can see from this graph, and these points, we found that the potential difference increased at the battery, which due to EMF, and only decreased at the 2 resistors, and everything else had a 0 potential difference. And this reinforces the loop rule because it shows that if you add up all the potential differences, it would be equal to 0. And the reason that the ammeters in our ideal experiment did not affect any of the potential difference calculations is because they have 0 resistance. As you can see that there was no potential difference change at G to H where the ammeter is. It's because the ammeters have 0 resistance. In the next part of the experiment, we created a parallel circuit around the 100 ohm resistor, and the potential difference at the 100 ohm resistor was equal to 0. And we can also see that the amps increased by 0.04 once we added the parallel circuit. And the reason is because the current usually takes the path of least resistance. And since there was least resistance, the current increased, since current and resistance are inversely related. In the next part of the experiment, we had to calculate resistance at different points of the loop, and at the 47, we would use the potential differences we found in the previous section to find the resistance at certain points, and we found that the resistors had almost exactly the same value due to some rounding issues, but they were not exactly the same, but they are practically almost the same. And the resistance in the wire is equal to 0 ohms, and the resistor in the ammeter is 0 ohms. In the next part of the experiment, we were learning how to use capacitors, and we found that if a battery is attached and charging the capacitor, it takes and with a resistor of 10 ohm, with a resistor of a 10 ohm light bulb, it took 18.16 seconds, and if we attached a 20 ohm light bulb, it took 20.26 seconds for the capacitor to fully charge. And to fully discharge a capacitor with using a 10 ohm light bulb, it would take 39.64 seconds, and a 20 ohm light bulb would take 40.08 seconds to fully discharge a capacitor. Next part of the experiment, we've found we were charged with the task to find the time constant of and how we did it was we used this formula that was given to us. Change of voltage equals V naught e to the power e to the negative t over RC, RC being the time constant, and we derived this equation. And if we were to plot the natural log of change in voltage divided by voltage naught by t, we would be able to find a slope which would equal 1 over RC. And if we were to inverse the slope, we would get 6.02 seconds as our time constant. And so additional questions we had in this lab were, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What different about a real ammeter, and how would it have affected the circuits you hooked it up to? The ammeters in the simulation have zero resistance, and a real ammeter has slight resistance, so the current measurement would be lower. And what if you were doing this lab in real life and used a battery to charge a real capacitor with no resistor in the circuit? How quickly would our model predict the capacitor to reach full charge? Would this prediction happen in real life? So in the ideal model, the capacitor would reach full charge pretty quickly, but in the capacitor in the real world would take longer to charge than the ideal model, because no capacitor would charge instantly in real life, because all circuit components have the slightest resistance.